October 4th, 1957. A metal sphere the size of a beach ball begins to beep in the darkness above the atmosphere. Sputnik. The Soviet Union had beaten America to space, and in Washington the panic wasn't just about pride, it was about gravity. You see, getting to space is hard, but getting anywhere in space is almost impossible. It's because of a rule written by Isaac Newton and enforced by the laws of chemistry. It is called the tyranny of the rocket equation. To go somewhere, you have to burn fuel. To carry that fuel, you need a bigger rocket. To lift that bigger rocket, you need more fuel. It is a vicious cycle that strangles our dreams of the stars. Even the mighty Saturn V, the machine that took us to the moon, was 96% fuel and tank. The astronauts, the capsule, the life support, that was less than 4% of the weight. We were barely skimming the surface of the ocean of space in a canoe made of aluminum foil. But in 1958, a group of physicists in a dusty laboratory in San Diego decided to cheat. They looked at the atomic bomb, the weapon designed to end civilization. And they asked a question that sounded like madness. What if we didn't use it to kill people? What if we used it as gas? They didn't want to burn fuel. They wanted to ride the shockwaves of nuclear Armageddon. They designed a spaceship the size of an ocean liner. A ship that could carry 100 men to Mars in 4 months. A ship that could reach Saturn by 1970. This wasn't science fiction. It was funded by the US Air Force. They built the models, they tested the engines, they even picked the pilots. This is the story of Project Orion. The spaceship that was powered by atomic bombs, the machine that would have given us the solar system, if it didn't poison the Earth first. Welcome to Shadowworks. To understand why anyone would be crazy enough to put a nuclear bomb under their seat, you have to understand specific impulse. In simple terms, specific impulse is the gas mileage of a rocket. It measures how efficiently an engine turns fuel into thrust. The best chemical rockets, like the Space Shuttle main engines, have a specific impulse of about 450 seconds. That is the absolute limit of chemistry. You cannot get more energy out of burning hydrogen and oxygen. It's a physical wall. To get to Mars with chemical rockets, you need a ship that is mostly fuel tank. You float there for 8 months, your bones dissolving in zero gravity, praying your life support doesn't fail. Enter Stanislaw Ulam. He was a Polish mathematician, a genius, and one of the fathers of the hydrogen bomb. In 1947, Ulam was looking at the data from nuclear tests. He realized that a nuclear explosion doesn't just create heat, it creates propellant. The debris from the bomb moves at thousands of miles per second. If you could capture that energy, if you could channel it, you wouldn't get a specific impulse of 450 seconds. You would get a specific impulse of 10,000 seconds. With that kind of power, you don't need to build a canoe. You can build a battleship. You could build a spaceship weighing 4,000 tons. You could pack it with steel beams, heavy shielding, libraries, barbershops, and machine guns. And it would still accelerate faster than a dragster. It was the holy grail of propulsion. There was just one small problem. How do you survive setting off a nuclear bomb 10 feet behind your back? The project was formally established in 1958 at General Atomics. The codename was Orion. The team was a collection of the smartest people on the planet. You had Freeman Dyson, a theoretical physicist who saw the universe in equations. You had Ted Taylor, a man who designed the smallest and most efficient nuclear warheads in the US arsenal. Their challenge was engineering a way to ride an explosion without being vaporized. The solution they came up with was brutal in its simplicity. The pusher plate. Imagine a giant steel plate, dozens of feet wide and inches thick. This plate is attached to the bottom of the spacecraft. Between the plate and the ship, you have massive shock absorbers, giant pistons filled with compressed nitrogen. Here is how the drive worked. The ship drops a pulse unit, a specialized nuclear bomb, through a hole in the center of the plate. The bomb falls about 200 feet behind the ship. It detonates. But this isn't a normal bomb. It is a shaped charge. The casing is made of tungsten and beryllium oxide. When it explodes, it channels the plasma into a focused jet, a spear of nuclear fire aimed directly at the pusher plate. The plasma hits the plate at 100,000 miles per hour, The plate glows white-hot for a millisecond. The force kicks the plate forward. The shock absorbers soak up the blow, converting the violent kick into a smooth acceleration for the crew. Then, 1 second later, clunk, another bomb drops. Flash, clunk, flash, clunk, flash. It was an engine that sounded like a jackhammer, a nuclear heartbeat. To reach orbit, the Orion would have to detonate 800 nuclear bombs in the atmosphere. Just think about that image. A 4,000-ton steel skyscraper rising from the Nevada desert, riding a staircase of 800 nuclear explosions. The noise would be deafening. The light would blind anyone watching from 50 miles away. It was magnificent, and it was absolutely terrifying. You might think this was all just paper theory. It wasn't. They built it. In 1959, the team built a flying prototype called Put-Put. It didn't use nukes, obviously. It used conventional C4 explosives. They took it out to Point Loma in San Diego. They fueled it up. They started the timer. Bang, 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 bang. The model shot up into the air, stable as a rock. It worked. The concept of pulsed propulsion wasn't a fantasy. You really could fly a ship by blowing it up repeatedly. Ted Taylor and Freeman Dyson began to dream big. They weren't interested in just getting to the moon. The moon was boring. They drew up plans for a mission to Mars. Target launch date, 1965. Then, a mission to the moons of Saturn. Target launch date, 1970. They designed a Super Orion, a ship that weighed 8 million tons. A ship that could carry a city, a ship that could reach Alpha Centauri, the nearest star, in 100 years. For a brief moment in the late 1950s, humanity stood on the edge of becoming a true interstellar species. We had the tech, we had the math, we had the bombs, but we also had the Cold War. While General Atomics was dreaming of exploration, the Pentagon was dreaming of domination. The U.S. Air Force got wind of Orion, and they didn't see a science vessel. They saw the ultimate warship. General Thomas Power, the head of the Strategic Air Command, famously said, "Whoever controls Orion will control the Earth." The Air Force drew up plans for an Orion battleship. A deep space dreadnought, it would be armed with 500 nuclear warheads. It could hover over the Soviet Union, immune to interception, and rain down fire at will. But the Soviets weren't asleep. Across the ocean, Soviet scientists were reading the same physics journals. Andrei Sakharov, the father of the Soviet hydrogen bomb, was exploring similar concepts. They called it explosive propulsion. The Soviet Union had a different approach to nuclear power. They believed in brute force. In 1961, they detonated the Tsar Bomba, a 50-megaton monster. Rumors began to circulate in the CIA that the Soviets were building their own pulse drive. The fear was palpable. If the Soviets built an Orion ship first, they wouldn't use it to go to Saturn. They would park it over Washington, D.C. This paranoia fueled the project, but it also poisoned it. By turning Orion into a weapon, the Air Force made it a target. And the biggest enemy Orion faced wasn't the Soviet Union. It was the atmosphere of Earth. There was a dirty secret at the heart of Project Orion. Every time the ship launched, it would detonate hundreds of nuclear bombs inside the Earth's atmosphere. Freeman Dyson, the conscience of the project, ran the numbers. He calculated the fallout. Even using the cleanest tactical nukes Ted Taylor could design, the radiation released by a single launch would eventually cause fatal cancers around the world. Dyson came up with a grim statistic: 1 death per launch. For every Orion ship that left Earth, somewhere, sometime, one person would die of leukemia or thyroid cancer caused by the fallout. If they launched a fleet, thousands would die. The team tried to solve it. They proposed launching from platforms in the ocean near the Antarctic. They proposed using massive chemical boosters to get the ship out of the atmosphere before turning on the nuclear drive. But the stigma of the bomb was too strong. In the early 1960s, the world was terrified of nuclear testing. Strontium-90 was being found in baby teeth. People were building fallout shelters in their backyards. The idea of a spaceship that literally sprayed fallout as its exhaust? It was a political nightmare. The end came with the stroke of a pen. In August 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Test Ban Treaty. It outlawed all nuclear detonations in the atmosphere, underwater, or in outer space. There was no exemption for peaceful exploration. There was no loophole for Project Orion. The treaty was designed to stop the arms race, to stop the poisoning of the planet. But in doing so, it killed the only technology capable of taking us to the planets in our lifetime. Freeman Dyson later wrote that the treaty was a good thing. It saved the Earth from being turned into a radioactive wasteland, but he also mourned what was lost. The project lingered for a year or two as a theoretical study, but without the ability to test, it was a zombie. In 1965, Project Orion was officially cancelled. The team dispersed. Ted Taylor went on to become an anti-nuclear activist, horrified by the efficiency of the bombs he had designed. The blueprints were stamped classified. The models were dusted off and put in museums, and NASA chose a different path. They chose the chemical rocket. They chose the Apollo program. Apollo was a triumph of engineering, but it was a dead end. Once we went to the moon, the Saturn V was retired. It was too expensive. It was too inefficient. If we had built Orion, we wouldn't have just visited the moon. We would have built a base there. We would have mines on Mars. We would have research stations on the moons of Jupiter. We traded the solar system for a clean atmosphere. It was probably the right choice, but it was a choice that grounded humanity for the next 60 years. But what about the Soviets? The user manual for the Cold War says that for every American project, there was a Soviet shadow. While Orion died in the US, the dream of nuclear propulsion didn't die in the USSR. The Soviets focused heavily on nuclear thermal propulsion, a different beast. Instead of exploding bombs, they used a nuclear reactor to superheat hydrogen gas. It was safer, cleaner, but less powerful than the pulse drive. But recently declassified files suggest that in the dying days of the Cold War, the idea of the pulse drive returned. In 1987, the Soviets launched the Polyus spacecraft. It was a prototype orbital weapons platform. Some speculate it was the first step toward the kind of large-scale military structures that Orion would have made possible. But like the N-1 moon rocket, the Soviet efforts were plagued by complexity and a lack of funds. The Soviet Orion, mentioned in whispers, was likely a mix of Western paranoia and the very real work of Sakharov. But they faced the same physics and the same treaty. The irony is that the Test Ban Treaty, signed by the Soviets, stopped them from building the very weapon the Americans feared they were building. Today, Project Orion is a what-if story. A phantom timeline where humanity took a different path. It represents the ultimate paradox of the atomic age. The same force that can destroy cities is the only force powerful enough to give us the stars. We chose safety. We chose to stay in the cradle. But the physics hasn't changed. The math is still true. The blueprints are still there. Someday, if we ever face an extinction-level event, an asteroid, a dying sun, a collapse of the ecosystem, we might have to open that dusty file again. We might have to make a deal with the devil. We might have to ride the bomb, because in the cold vacuum of space, the only thing that matters is energy. And nothing, absolutely nothing, has more energy than the fire of the atom. I'm Shadowworks. If you want to see what happens when the Soviets actually tried to build a nuclear nightmare, click on the video about the Bink Caspian Sea Monster, the giant ground effect vehicle that baffled the CIA, or check out the story of the Beak SR-71, the plane that leaked fuel on purpose just to survive Mach 3. Subscribe to the channel. We are digging up the secrets history tried to bury. And clear your baffles. I'll see you in the next one.